fundamentally, we're going to be mostly concerned with measuring physical quantities. To do that, usually we're attaching some sort of number and some sort of unit on those quantities. So just so we have our vocabulary clear. Well, say I'm measuring something like the height of an object. Well, in this case, the height would be the physical quantity that I'm measuring. Now, anytime you take a measurement, there's going to be some uncertainty with that. Nothing is ever completely precise. It depends on, am I measuring the height of a person at the top of a mountain, or on an airplane, or at sea level? All of those heights are going to change a little bit just based on the conditions around. Depends on temperature, a bunch of different things. So suppose you're measuring height, that's the physical quantity. We're always going to be assigning some sort of symbol or variable to that physical quantity. The symbol is more just kind of like a nickname, so that when we're doing our algebra, we can use a shorthand. We don't have to write out height every time. So usually we try to pick a symbol that matches the variable name. So for height, I might take the symbol h. That's not always going to be able to work because eventually we're going to run out of letters. We'll have to get into Greek letters. But usually, as much as possible, we're going to try to find some letter that matches the physical quantity in some way. Up next, we want to get some numerical value for that quantity. So let's say we measure the height of an object, and let's say we get 3 centimeters. Now we have to pay some attention to the uncertainty, right? Because it's not exactly 3 centimeters. Maybe it's 3 centimeters when you measure it the first time, but maybe it's 3.1 when you measure it the next time. Maybe it's a little bit hotter, and then things expand as they get hotter, so the height is going to change. So for that reason, we're going to record some uncertainty with that physical quantity. So let's say it's 3 centimeters plus or minus 0.1 centimeters. Well, I also have to specify that there is a unit that we're also measuring. In this case, the unit is centimeters. Now, units are there to provide some sort of standardized context. What do I mean by standardized context? Well, we want something that anybody anywhere in the world can look at and say, well, I know what they mean here because I know what a centimeter is. So in olden days, you used to measure things with a king's foot. That's where we got the foot from. But king's feet have a tendency to change size, so that's not a particularly standardized measurement. In this case, we're going to be using meters and centimeters. And we might talk a little bit more about exactly where those units come from. But for now, let's just take a centimeter to be a little bit less than half an inch. When you write numbers in scientific notation, it's very easy to see roughly how big the number is. The reason is, so let's take an example. Say I have a number like 3.5 times 10 to the 4. 10 to the 4 tells me how big that number is. Specifically, the 4, which we call the order of magnitude, gives me a rough idea how big that number is. 10 to the 4 is about 10,000. To contrast that, 10 to the 5 is about 100,000. Not about, it is 100,000. 10 to the 6 is a million. 10 to the 9 is a billion. Every time that number changes, every time it goes up by 1, your total number goes up by 10. If it goes up by 2, your number goes up by 100. So by changing this number, I change the magnitude, by changing this 4, I change the magnitude of your physical quantity here by a very large degree. We call how big this number is, again, the order of magnitude. To give you some practice visualizing different orders of magnitude, it's helpful to build a little roadmap of different markers where we can say, well, this is about what 10 to the minus 9 means, but this is what 10 to the minus 6 means. So let's just try to visualize these things. So 10 to the minus 9, that is the nanoscale. So if you've heard of nanotechnology, it's dealing with things on a nanometer size scale. So nano just means 10 to the minus 9. You can think nano 9. And the nanometer size scale is roughly the size of molecules. So if I look at the width of a DNA molecule, typically I'm going to be measuring that in nanometers. So the width of a DNA molecule is about 2 nanometers. If we go up by a factor of 1,000, so 10 to the 3, going from 10 to the minus 9 to 10 to the minus 6, now we are on the microscopic size scale. This is the size scale that's just on the edge of what we can see with a microscope. So if I look at things like biological cells, so paramecium, bacteria, those kinds of things, they're about 10 to the minus 6 meters, or micrometers. 1,000 times bigger than micrometers is millimeters. Millimeters we have experience with because we've all looked at meter sticks. We've seen the millimeter size scale. Millimeters are 10 to the minus 3. Milli is 1,000 times smaller. So that's typically things like small bugs. You can see what a small bug is. They're going to be at the millimeter size scale. If we get into meters, then we start measuring things like people. So a typical human, a tall human, might be 2 meters tall. A short human, like a small child, would be about 1 meter tall. But that size scale doesn't get its own prefix because that's the base size scale. That's 10 to the 0. Anything to the 0th power is just 1. Going in the opposite direction to larger things, again starting at people, 10 to the 0, we go up by a factor of 1,000. By 10 to the 3, we get to 10 to the 3. That's kilo. A kilometer, or a kilometer, is about the size of Simpson campus. So it's not quite a mile if you're talking about kilometers. Moving on to 1,000 times bigger, we get to mega, 10 to the 6. So that's 1,000,000 meters. That's roughly the distance across the continent. So from California to the East Coast, you might measure that in megameters. If we start getting into gigameters, that's 10 to the 9. That's like the Earth to Moon distance. So the distance from the Earth to the Moon is about 1/3 of a gigameter. We could keep going with this for bigger and bigger numbers. There are more prefixes. These are the common ones that you hear a lot. So these are the ones that I'm going to expect you to know. One other one I will expect you to know is centi. So centimeter. Centi is 10 to the minus 2. This one's pretty common because it's about the size of an inch, or roughly the width of one of your fingers. When we talked about uncertainty, we said that all numbers that we measure have some uncertainty to them. No measuring device is absolutely correct, and even if it were, the size, the mass, time, these things change. They fluctuate over time. Any physical quantity, so for example, my height is different in the morning than it is in the evening because gravity has been pulling me down. So there is no such thing as a completely precise, exact measurement. Quantities change all the time. To the extent that there's always some uncertainty, we want to be able to get comfortable with that uncertainty. In fact, we want to get so comfortable that we don't care about being exact. Because once we get over the fear of having the numbers be exactly correct, we can start to make estimations. And estimations are a very useful tool. We've talked about orders of magnitude, figuring out roughly how big some physical quantity is. We should be able to estimate, and I'm going to expect you to be able to estimate any physical quantity to within an order of magnitude. So that's power of 10 above or below. Now, for example, if you were going to estimate my height, you might say, Santos, you're about 6 feet tall. Now, an order of magnitude estimate would say that I am somewhere between 10 times smaller than that and 10 times bigger than that. So somewhere between 0.6 feet, about 6 inches, or 60 feet. So somewhere between 60 feet and 6 inches is my actual height. Right? You should be able to estimate that. Knowing a person's height is somewhere between 6 inches and 60 feet is probably not very useful. But when we can conceptualize numbers of different sizes, that does become very useful. So for example, if you want to know the number of stars in a galaxy or the number of cells in a human body, knowing that number to within the uncertainty of within an order of magnitude, that's a very useful number to know. So we want to be able to make these kind of estimates. We want to be able to think logically about a problem and find a mathematical route to estimating what the final answer is going to be. And I want to pay particular attention to conceptualizing how big numbers are. So a lot of times if you hear numbers in the news, for example, government program X is going to cost $1 billion. Government program Y is going to cost $1 million. Well, to many of us, those just seem like big numbers. So, well, we don't want people spending that amount of money. Well, how much money is that actually? Does $1 million matter? Does $1 billion matter? Does $1 trillion matter? To give you an idea of how different these numbers are, let's just consider what a billion seconds is going to be. So 1 million seconds, how many, put that into context. How long is 1 million seconds? 1 million seconds is about 1.5 weeks. 1.5 weeks, not too long. What about 1 billion seconds? 1 billion seconds, say you want to wait 1 billion seconds, you would be waiting 31 years. 1 billion seconds is about 31 years. So 1.5 weeks for 1 million seconds, 31 years for 1 billion seconds. What about 1 trillion seconds? Well, a trillion is 1,000 times bigger than 1 billion. So it's going to be 1,000 times 1 billion seconds. 1,000 times 1 billion seconds is not 31 years, it's 31,000 years. 31,000 years for 1 trillion seconds. So at the dawn of man, that is 1 trillion seconds. Okay, so these numbers are very different. So when you hear government program costs X, where X could be 1 million, 1 billion, or 1 trillion, those are very, very different numbers. And you want to be able to pay attention to exactly how big those numbers are. Order of magnitude estimates can seem scary at first, but if you sit down and think about them for a little bit, all of a sudden you realize they're not that hard. We can just use logic to come to an answer. So let's try to do that. This is a problem that students gave me last year. It seems like it's impossible at first, but let's see if we can actually do it. So the problem is, how big of a sand castle could you build if you used all of the sand in the world? Step one for doing estimates. Start with what you know. So what do I know? I know sand is usually found on beaches. So let's look at the beaches. Let's see if we can figure out how much sand there is on a typical beach. Well, let's consider the eastern seaboard of the United States. So if I look at the eastern seaboard, let's write down what I know. Well, if I look at a map, I can get a rough estimate of how big that is. And you'll find it's about 2,000 miles. So the distance from the top of the eastern seaboard of the U.S. to the bottom is about 2,000 miles. How wide is a beach? Well, it's going to vary. Some beaches could be miles wide. Some beaches could be only a few feet wide. Some beaches are going to be rocky and not have any sand. As a rough estimate, I'm going to say 100 feet. I say this because having grown up on the East Coast, most of the beaches are fairly small. Beaches in California are a bit bigger. Rough estimate, 100 feet. Now, some beaches are going to be 1,000 feet. Some beaches are going to be 5 feet or no feet, whatever it happens to be. We're going to say 100 feet for our width. How deep is the beach going to be? Right? How far can I dig before I hit something that's not sand anymore? As a rough guess, I said 10 feet deep. Now sometimes you start digging a sandcastle, you hit rock very early. Sometimes it's much deeper than that, but I'm pretty sure it's not going to be 100 feet. And usually you can dig down at least a foot before you start to hit something that gets very rocky. So I said 10 feet of sand. Another thing I want to know is, so far I've only considered the eastern seaboard of the United States. Well, that's not the only place where I'm going to find sand. Right? There's going to be a lot more places I can find sand because there's a lot of different beaches that you could go to. So let's say I take my 2,000 meters and then I go here, and I go here, and I go here, and I go here. And I keep doing that all around the North and South American North and South American continents. And then I do the same thing on the European and African and Asian continents. I keep going and I go to all the different beaches and I get a rough estimate using the eastern seaboard as my meter stick for how many beaches there are going to be that are about this size. And when you do this, I just took a globe and looked at the globe and kind of measured out, got a rough estimate. And I found there's about 50 seaboards that are about the size of the eastern seaboard in the world. There's about that many of them in the world. A decent estimate. When I counted, pretty sure it wasn't 500, and it was a lot more than 5. So 50 seems like it's a pretty good estimate. All right, we started with what we know. The next thing we want to do is check to see if our estimates are reasonable. So if you're unsure about the guesses that you've made, what you can do is look and say, well, if I go 10 times bigger than this, what do I get? If I go 10 times smaller than this, what do I get? Are those numbers unreasonable? Right? 10 times bigger is unreasonably large, and 10 times smaller is unreasonably small. There's a good chance that my number is a pretty good fit. At the very least, it should fit within an order of magnitude, i.e. to within a factor of 10. So for my eastern seaboard guess, I didn't even have to go a factor of 10 times too big. I could just look at a map. 1,000 miles was too small, and, 1,000 miles was too small. 4,000 miles was going to be too big. Okay? So 2,000 seems like a pretty good estimate. We're doing kind of the Goldilocks rule here. My porridge is too hot, my porridge is too cold. The one in the middle is just right. So 50 eastern seaboards per world. If you look at a map and you just kind of count them off, 500 is way too big, unrealistically large. 5, way too small, unrealistically small. 50 is a pretty good number if you count it out. What about the width of the beach? I said 100 feet. Well, 1,000 feet, that's like a quarter of a mile. So 1,000 feet is, it's going to be like half or 3/4 of the way around a track. Most beaches are smaller than that. California has some big beaches, but most beaches are going to be pretty small. So 1,000 feet, probably way too large. 10 feet, probably way too small. Something in the middle, again, the Goldilocks rule, something in the middle is going to be just about right. What about the depth? I said about 10 feet before you hit something rocky. Again, I've dug sandcastles before. You can usually go a foot down and not hit anything. 100 feet seems like it's going to be too big. Eventually you're going to hit some sort of rocky surface. So 10 feet deep seems like a decent estimate. Now, any of these could be a little bit off. We don't care if they're a little bit off. We care about big orders of magnitude off. If I multiply these all together, and some of them are a little too big and some of them are a little too small, on average, those things are going to cancel out. So we should still end up with a pretty good estimate. The final step in doing an order of magnitude estimation is to multiply your quantities so that the units cancel and gives you the dimensions of the quantity that you want. We're just doing dimensional analysis here. We're going to multiply a string of physical quantities together and find out what we get. So here's how I set this up. We said we had 2,000 miles across the eastern seaboard, so 2,000 miles per eastern seaboard. We said there's about 50 eastern seaboards worth of beach across the world. We said the beaches were about 100 feet wide and 10 feet deep. Let's see if that gives us the right units. Well, let's see. Eastern seaboard seems like kind of a funny unit, but it's just a unit like anything else. And like any other unit, I can cancel it out and treat it just like a normal variable. And let's see, I'm going to be left with miles times feet per world. So I'm going to get distance times distance times distance, some sort of volume in the world, per world. It's going to be the volume of sand in my world. Now, miles feet squared is kind of a funny unit for volume, so you want to do some conversions here. The good news is you don't have to do that by hand. If you just type in 2,000 miles times 100 feet times 10 feet, and you plug it into Google, it'll do the conversions for you. When you do that, take 2,000 times 50, or 2,000 miles times 50 times 100 feet times 10 feet, you will get, I'm plugging this into Google, about 10 to the 10 meters cubed. So we can write this, oh, I should say per world. So we can write the volume of sand is about 1 times 10 to the 10 meters cubed. It's my total volume of sand. Now if I were to build a sand castle out of that sand, let's put some spires on our sand castle. Let's give our sand castle a drawbridge. Every sand castle needs a moat. Here's our sand castle. Now, I know it has a total volume of 10 to the 10 meters cubed. How tall of a sand castle would that be? Well, if I assume my sand castle is roughly the shape of a box, I know that the volume is the height times the length times the width. And if those are all the same, I can get any one of them just by taking the cube root of the volume, because volume is length cubed. And when I do that, you would find that you have a sandcastle that is 2.5 kilometers tall. That's a very big sandcastle. Now, notice if I had just asked you this question on the street, you'd have been like, Santos, you are crazy, and started backing away slowly. But in the context of this class, or in the context of your future life, if you want to figure out anything, all you have to do, if you want to figure out any physical quantity, all you have to do is just remember, let me think logically, what do I know? How can I build a path algebraically to the answer? And then you want to check yourself. You want to say, all right, are my estimates reasonable? What's 10 times too big? What's 10 times too small? And if your number fits that Goldilocks rule, you know your final answer should be roughly correct, should be correct to within an order of magnitude.